Hey guys, this is Mrs. Tran-Bloom. I'm going over the second exploration in your 2.5 note. We started in class, okay, but I'm just going to go over from the beginning just in case some of you were absent on Wednesday. Okay, let me just look for two different color pens really quickly. So second exploration, I want you to graph all of these right here on the same screen, okay, of your calculator. But because I don't have a calculator, I'm just going to graph each one by hand. And yes, you can always graph things by hand. So the first one I'm going to graph is this piece right here, which I'm using a red pen. This is what's called a parent function. This is your parent function, y equals square root of x. I'm going to make an input and output for it. If you have already seen this in class, it does not hurt to listen to it again, because again, this is one of the concepts that is so difficult. Students always forget or make the most mistakes on, okay, which is this one skill right here. So my input is when x is 0, square root of 0 is 0. When x is 1, square root of 1 is 1. When x is 4, the reason I picked 4 because it's a nice square number. Square root of 4 is 2. So those are my input-output table. Make your dots. Make sure I can clearly see your dots. 2, 4. Okay, so this go all the way. Let's label y subscript 1. I'm gonna get I have a black pen. Let's see if I can have a blue pen to, because I have 3 different functions here. I want to be able to show you what each one is supposed to be or each one is supposed to look like. How about I'll do a pencil and then I'll highlight with something else on it. Okay, so that's my first one, the parent function. The next one I'm going to use is a black pen for this second piece right here. This is y subscript 2. That means I'm about to give you a second equation. Equals to f of 2x. So this is your new input. So instead of having an input of an x, my input is now 2x. Okay, so if I just want let's just say that I don't even have a radical function here. I could just have any function. I can just say, hey, a function of 2x, what does it really mean, right? What is it doing to the function of my original x? So this right here is telling the reader, hey, you know what? You're about to change your input right here. So what is that going to be? So since I'm using a radical function, I'm going to create an input-output table again. Okay, so there's x, y subscript of 2 equals square root of 2x. So this is my... So in class, we talked about keeping the outputs exactly the same, 0, 1, and 2. Or one of the classes, we use 0, 1, and 9. It doesn't really matter. If I want my output to be 0, okay, I need to solve for x, so put 0 in. When y is 0, I'm going to square both sides. That's still going to give me 0. Divide both sides by 2, x is still going to be 0. Okay. So if my output is 1, what would my input be? So let's talk about it. Y is 1. So now again, I'm going to square both sides, get rid of this. I'm trying to solve for x. Then after squaring both sides, I'm going to divide by 2. So I'm going to end up with 1/2. Let's check it really quick. Okay, I'm just going to zoom in. Give me a second to zoom in. There you go. Let's check. 1/2 times 2 is 1. Square root of 1 is 1. So we're doing just okay. Okay, let's get the input because I want to know, hey, what input do I need to have an output of 2? So when y is 2, I need to solve for x. So I'm going to square both sides. If I square both sides, 2 squared is going to be 4. Then if I have 4 equals 2x, then divide both sides by 2. 4 divided by 2 is going to be 2. Okay, so check those out. Let's check my answer. 2 times 2 is 4. Square root of 4 is going to be 2. So those are the outputs and input for the second equation. Let's plot those. When x is 0, y is still 0. When x is 1/2, y is now 1. Look at that. Okay. When x is 2, y is now 2. I have something that's above my parent function. So this is now called y subscript of 2. So let's compare. Let's compare these two tables. Notice how the outputs are identical, but what's happening with the inputs? This input table right here, all the values are half as large, okay? All the values right here are half as large as my parents. So when you have 2 inside the equation, okay, then I'm shrinking, okay, notice how horizontally? Look at these dots. It used to be here, now it's here. Horizontally means on the x line, okay? Horizontally, I'm shrinking it by half, okay? So keep that in mind. When I multiply my x by 2, I'm actually shrinking my graph, right? We're going from here, shrinking it by half the distance. So what we need to understand is this. And so what happens if I take this reciprocal, okay? So take the 2 and take its reciprocal. So that's now a half, okay? So that's what I'm in essence doing. I'm horizontally compressing it by a half, okay? And let's compare this third equation right here. Input and output, x, y subscript of 3 equals to 1/2 x under the radical. And I'm going to use a pencil, and then I'm just going to highlight it with a different color. So I'm going to, again, keep my outputs exactly the same, okay? 0, 1, 2. So what would I need so my output can be 0? This one is still going to be 0. What would I need so my output can be 1? Let's put 1 into the y. Y equals square root of 1/2 x. Square both sides. So 1 square is still 1. Now I have a half x, and I want to solve for x because that's the input. So that means I'm going to multiply by 2 to both sides. So now 1 times 2 is 2. Okay. Similarly to this, this is my output. So substitute y value. So 2 equals square root of 1/2 x. I want to get rid of square symbol, the square root symbol, because I want to solve for x. So square both sides. 2 squares 4. Then I need to get rid of this half by multiplying both sides by 2. So 4 times 2 is going to be 8. Let's quickly check these two answers. So 2 times 1/2 is going to be 1. Square root of 1 is 1. 8 times 1/2 is going to be 4. Square root of 4 is going to be 2. Okay, so now let's compare this table with the parent. We are always going to compare the changes to the parent, okay? What's going on with all the inputs? All the inputs. What's going on? Does it look like it's twice as large or twice as long? Let's plot it to see visually on the graph, okay? When x is 0, y is still 0. When x is 2, I'm going up at 1. See that right there? Remember, the parent function is in red. It was used to be here. Now I'm twice as horizontally longer. When x is 8, I'm only going up to 2. So 2, 4, 6, 8, I'm going to 2. Okay. Remember, the parent, the y value is 2 is right here. Notice how I'm going way longer. So this is my y equals y subscript of 3. Okay. So notice how horizontally I'm pulling it this way. So that's a horizontal stretch. But look what's happening to my x. What's being multiplied to my x? 1/2 is being multiplied to my x, right? But what happens if I take its reciprocal? I would have a 2. So that's why this is twice as long. Okay. So we're going to spell out what I want you to do here. Okay. So this one says that in the argument, if the argument x of a function, okay, let's give this function any function it wants to be. Oh, let me zoom. Okay, ooh, there you go. If the argument x of a function f is y equals f of x, that means it can be anything it wants to be. Okay, it's multiplied by a positive number. Let's call it a. Okay, let's multiply by a positive number. Let's call it a. the graph of the new function, the new functions are y subscript 2 and y subscript 3, is obtained by doing what to the parent? Okay, so we're gonna say is obtained by multiplying each x coordinate of the parent y equals f of x by a value of 1 over a, whatever a was. Okay, so over here my a was 2, so 1 over 2, that would be by a half. So that's why on y subscript 2 we multiply my parent function, all the inputs, by a half, so I'm half as short. Then if you look at this right here, my a is a half, so 1 over half becomes a 2, okay? So remember, and whenever you're dividing a number by 1, all you got to do is flip it. So 1 divided by half is really 2. So from the parent to the third, to y subscript 3, I'm multiplying by 2, so that's why I have it twice as long. So we're multiplying by 1 over a. We call it horizontal. So we call it horizontally compressed, or compression. Let's write compression. Horizontally, or let's see, I want to horizontally. I've already used horizontally. Let's do compressed with the ed. We call it horizontally compressed if a is greater than 1. Okay, so over here, a is 2. That means it's bigger than 1. So this would be a horizontally compressed by a factor of 1 over 2, which is by a half. And we call it horizontally stretched if a is in between 0 and 1. Okay, that means I can have 1/2, 1/4, 3/4, 9/8, not 9/8, I'm sorry, that's greater than 1, 8/9, so on and so on. Okay, so over here, a is 1/2, so that's a horizontally stretched by a factor of 2 because I need to flip it. 1 over a means I need to flip this a value. So let's spell this out. Okay, so in our example, i.e. y subscript 2 is horizontally compressed by a factor of 1/2 fraction. Okay, then y subscript 3 is horizontally stretched by a factor of 2. Okay, so keep in mind, we need to, when we say this factor right here, and if it's getting stretched or getting larger, it needs to be greater than 1. If you are saying that's getting smaller, it's getting compressed, that means the factor, what you're going to multiply, needs to be less than 1 but greater than 0. Okay, so go ahead. You need to hit pause if you're not done. Okay, so hit pause if you're not done because we're moving on to the next example. Okay, example 1. And again, if I'm going too fast, you really do need to hit pause, okay? And finish writing and then play again. Example 1. The graph of y equals f of x is given below. That means this is the original function, the parent function. Use this graph to find both of these parts right here. Okay. So we have already done 2 explorations. One was dealing with the number that's being multiplied outside, and one was dealt with a number that's multiplying inside. Okay, so if we have a number that's being multiplied outside, it's going to give us a vertical change. So this is a vertical vertical change. Now the only question is it a vertical stretch or is it a vertical compress? Okay. Now when it's outside, it's going to make things larger. In this case, y values. Notice how this is 2 times f of x. That means 2 times y. So y is going to get larger by twice as much. So vertical stretch factor of 2. That means I'm going to take all of my y's and I'm going to multiply by 2. So here we go. Let's assume that this ends, okay? Let's put a dot right there for me. All right, so the first dot I have, I'm going to write all of my order pairs out here. 0, comma 0, pi over 2, comma 1. This dot is going to be pi, comma 0. This dot is going to be 3 pi over 2, comma, is that negative 1? Negative 1. This dot right here is 2 pi, comma 0. This dot above is 5 pi over 2, comma 1. And this last dot is going to be 3 pi, comma 0. So these are all of the x-intercepts and the local min and local max, okay? Because it says it's a vertical stretch factor of 2, that means I'm going to multiply all my y values by 2. So what happens when I multiply this by 2? It stays at 0. So what I'm going to do first is I'm going to write down all the x first, because all the x values, those values do not change. Okay, so let's write x first. This pi over 2, this is a pi, this is 3 pi over 2, this is 2 pi, this is 5 pi over 2, and this is 3 pi. Because it's a vertical change, the x, which is horizontal, those values do not change at all or take effect, okay? Or being affected. Okay, so here we go. Vertical stretch, that means only y values are changing. So 1 times 2 is 2. The word factor means we're going to multiply. 0 times 2 is 0. Negative 1 times 2 is negative 2. 0 again times 2 is 0. 1 times 2 is 2. 0 times 2 is 0. So these are my new points right here for this function. So these right here, okay, these points belong to that vertical stretch. So let's go and label. Because the x-axis is labeled by pi over 2, so that's what I'm going to do. Looks like they have 3 pi. 1, 2, 3. So let's make this a pi right here. This is 2 pi, and let's make that 3 pi. Okay. Let's go up. Let's see. This is 1, and this is 2. I'm changing the scaling of my graph. All right, let's go. The first dot is 0, comma 0. I'm using red to demonstrate my y equals 2 of f of x. 0, comma 0. Pi over 2 is right smack center. Go all the way to 2. At pi, I'm staying at 0. Okay, I'm plotting these right here. The third one is 3 pi over 2. That's 1.5 pi, right smack center. Go to negative 2. 2 pi, staying at 0. 5 pi over 2, that's 2.5 pi. Say right smack center, and looks like I already plotted that. I need to go all the way to 2. So 5 pi over 2, go to 2. And last dot, 3 pi, comma 0. So those are the dots. They need to look, the curvature of it will always be the same. So make sure you look at what was provided at the beginning and just copy that over. So that is a vertical stretch factor of 2. Okay. Alrighty then, let's go into this one. Now check this out. Y equals, do you see any number in the front? No, right? Look at this one. This is 3 times x, so you know the x is going to change. Okay, the horizontal stuff's going to change. Over here is y equals 2 times f of x, which is 2 times y. That means y is going to change. So with this, we know that x is going to change. But remember earlier when we were doing the exploration with the horizontal change, and when it's inside, we need to flip it. Okay? So because when we take its reciprocal, it's going to be 1/3. because it's 1/3, is going to be a horizontal compression factor of 1/3. Okay, so whatever the reciprocal is, that is going to be your the factor that we're going to multiply. Because it's horizontal, only the x is going to change. So I'm going to copy the dots again. Let's see, 1, 2, 3, 4, 5, 6, 7. I have 7 dots, so let's write 7 parentheses. 1, 2, 3, 4, 5, 6, and 7. Okay. Because only the horizontal is going to change, I'm just going to copy all the y values without changing it. All right. Okay, so the first y value is 0, 1, 0, -1, 0, 1, and 0. All right, let's multiply each x value by a factor of 1/3. So 0 times 1/3 is, oops, I should say still 0. Pi over 2 times 1/3. When you multiply fractions, you multiply across, so that's going to be pi over 6. Pi times 1/3, this is pi over 1 times 1/3, so it's going to be pi over 3. 3 pi over 2 times 1/3, these 3's will cancel. Okay, so you have a pi over 2. 2 pi times 1/3, this is 2 pi over 1 times 1/3, so that's 2 pi over 3. 5 pi over 2 times 1/3, 5 pi times 1 is 5 pi. 2 times 3 is 6. And the last one, 3 pi times 1/3. The 3's on the top and the bottom will cancel. I'm going to end up with the pi. All right. So look at this. This last point, notice how we have 3 pi. And then because we are compressing it by 1/3, we started from 0 to 3 pi. See, 0 to 3 pi. But because now I'm going to make it smaller by 1/3, the entire curve is only going to go from 0 to pi. So let's see what that looks like. Okay. I'm still going to keep this at pi, 2 pi, and 3 pi. And then this is still my 1, and this is still my 2. This is my -1 and my -2. All right. So what is that going to look like? My first dot, 0, 0, still there. Okay. Let's plot this last dot because that's really easy. 0, pi, comma, 0. So that's going to stay right there. The next dot, well, between 0 and pi, I have pi over 2. See that dot right there? I'm going to go down to -1. So I'm going to plot this dot. Right smack center, -1. Okay. Then a pi over 6. What that means is a pi over 6, we can also do a pi over 3. From 0 to pi, I have 3 boxes right here. That means 1/3 of a way is going to be pi over 3, and I'm going to stay at 0. Okay. So check that. And 2 pi over 3, so this is 0, 1 pi over 3, 2 pi over 3 is right here. I will also stay at 0. So all those 0 dots. Can you guys see that? Okay. All right, so the only two things I did not plot are these. Okay. Between 0 and pi over 3, halfway distance, half distance is going to be pi over 6. So right smack in the center, I'm going to go up to +1. Okay. And again, if that's 1 pi over 6, this is 2 pi over 6. Right in the middle is 3 pi over 6, which we already have 1/2. 4 pi over 6, which we already have 2 pi over 3. And the next one is going to be 5 pi over 6, and looks like I need to go up at +1. So there you go. Notice how small these dots are and how close they are. The reason they are so close to each other is because we compressed it, right? Look at that. The curvature of it should be exactly the same. But because we shrunk the entire graph, it just got smaller. Okay? And this one, look at the height, the top and the bottom, the local min and local max. The local max is still at 1. Local min is still at -1. It's just that we just got so much smaller. All right. So this is kind of the end of a video. If you didn't understand it, I really want you to listen to it again. Okay? So for the remaining of your homework tonight, I'm going to ask you to look at this right here. See this right here? Okay. I want you to look at it, estimate some points. Okay. Find these points right here. Make a list of all those points. And I would like for you to do this check for understanding and graph those right there. Okay, graph those right there. This is something that we just studied. This is a review, so I want you to think back from Algebra 2 what it means. So this is going to be on your own. So when I stamp this, I'm going to need to see both parts A and B to be completed. So on your own.